Good, good morning, everyone. This is Matt Webster. I'm going to be spending a half an hour to an hour with you on a little video lecture on data analytics and the path of progressing personally and as an enterprise towards data maturity. This will be one of the topics for our digital health track in 2024. For those of you not familiar with the program, Rocky Vista has the nation's first and leading longitudinal track for medical students. We have a group of about 24 DO students that are trying to incorporate health informatics and other digital health related technologies into their curriculum. And the faculty that we have here today with us from Rocky Vista University in Colorado and Utah is part of that effort. So my topic is to lead you through some of the basics of data formats and take you through a progression from the simplest building blocks through APIs and on to data analytics. What we'll do today is we'll have a sort of a pre-lecture, spend about a half an hour to an hour with you, taking you through some basic content and some hands-on examples. And then when we get into class on Tuesday, I will lead you through a review of this content, and then we'll do some real live data analytics with one of the new products that's out there, Amazon AWS QuickSight. So you'll get some deep hands-on experience in class, and we'll use this time out of class, sort of that flipped classroom model, so that you get the background you need so you can come to class prepared to do what you need to do to experience data analytics in real time. All right, so my objectives today and next week, give you some theoretical and practical experience with data formats, to get you hands-on and some experience with APIs or application programming interfaces, talk about data engineering, and give you a hands-on experience with data engineering software package called Tableau Prep. We'll segue from there into analytics, which is sort of the culmination of the hands-on effort with AWS QuickSight. And then we'll close out with some closing remarks and some theory that will help you position yourself within the larger industry and the movement that we have towards data analytics for individual practitioners and for the larger health or government or enterprises. All right, so some motivation. You may have already heard this one, but I'll spend maybe 5 minutes just trying to tee this up for those of you that maybe haven't heard this story and that are trying to figure out, how data analytics relates to your practice as an individual physician or to problems of public health. So before Game of Thrones, there was the original Jon Snow, who was a physician in early to mid 1800s London. So within the neighborhood Soho, I guess it was in 1848, there was an outbreak of cholera. So cholera was a horrible disease. I guess they still suffer from it in the third world. We largely solved the problem in the first world because we figured out the root cause. But back then, they weren't real sure what caused it. They just knew that you caught it in the morning and you were dead by the afternoon. So the general theory was that it was an airborne disease, but that wasn't really known how that was transmitted. But this Jon Snow character, he believed that it was a waterborne disease. So what happens here is that there's an outbreak in Soho in 1848, and he decides he wants to take a data analytics approach to this problem. So he gets out his pen and paper and his map of the neighborhood, and you can start see some of it here. He starts to chart out the neighborhood, and then he makes a little hash mark at each address where the symptoms were first noticed. So what he's doing there is he's geocoding patients into a certain location. So we are familiar with Google Maps and so on. They didn't have that back then, but they did have paper maps, and they were able to keep track of how many patients noticed symptoms at a given address. So this map, this is, I guess, a reproduction of his map. He was able to draw, some 500 or more observations of data onto his map. And so his theory that it was waterborne was supported by this map to some degree because he could see that the outbreak was clustered around certain points within the neighborhood. So he had the theory that the certain pump, this Broad Street pump, was the source of the disease. But by itself, I think it's very important to note early on in this exercise that just making a map and drawing some lines on the map, it doesn't necessarily mean much because even if it supports your theory, it may not be conclusive to the powers that be. In his case, he had to persuade the people in the neighborhood to do something about it, which actually proved to be quite a difficult problem even after he figured out what the cause was. So what actually happened is that the map, the analytic portion here, served as the basis for further investigation into was the pump the actual problem. And what the exercise shows us is it's not just the data collection, but it's the analysis and the filling in the backstory that really matters. So, for example, we do have outbreaks of cholera, but not everywhere around the Broad Street pump. It's not exactly, just a simple distance rule from the Broad Street pump. For example, the workhouse, there were 535 people in the workhouse, but they did not have cholera, even though they're right there by the pump. And there's a brewery, and they also didn't have cholera, even though they're right next door to the pump. So how do you figure this out when the data isn't telling you, what you want to know right up, hitting you over the head? Maybe it's not exactly a slam dunk. Well, that's where the analytics and the real work has to happen, because you have to dig into things like, why do you have these anomalies? In the case of the workhouse, it's because they had their own source of water there, right? In the case of the brewery, it's because they got free beer, so they drank beer instead of water, and they didn't have to use the pump. There are other pumps around the neighborhood. Why did people that buy those pumps still get cholera? Well, it's because they thought the pump from the Broad Street pump tasted better, or there was a pump that was on a dead-end street, so not many people used that one. So eventually they did realize that the pump was located by a cesspit, and they took the handle off the pump, and that led to a happy ending. But even after taking the handle off the pump, it didn't even necessarily solve the problem, because it didn't remove the cesspit. So you can have one step forward, another step forward, then maybe a step backwards. So data analytics, it is something that existed before computers. It's something that existed for the AWS cloud and big data. Physicians, have used these techniques in the past, and I think there's an important part of your toolbox. But my overall message to anyone, regardless of the particular PowerPoint or this presentation, is that critical thinking is essential. You can't just imagine that you're going to use data analytics and solve your problem instantly. You're going to have to go through all the grunt work. You can't be the drone, even if you have a DO after your name. So this little exercise here with the Broad Street pump, it's a story that everybody knows from epidemiology. It starts to get traction through videos on YouTube and NPR specials, but it is something that we can keep in the back of our mind, and probably a good story to dig into when you're thinking about how you would motivate other people to become involved in data analytics and see the value of going through this little journey that we're about to embark upon. All right, so that was the fun story to start the presentation. We're going to go into this next bit, which is starting to take a turn into the more technical. I want to make sure that you have basic familiarity and competency with the technical artifacts that you're going to run into as part of data analytics. So generally, we're referring to files that are containing data and that are in certain formats. So there are several file formats. You could think of them as the extensions that go at the end of the file that have emerged over the years, over the decades as standards. So for example, the top line, these are quote unquote text formatted files, or text files, comma separated formatted, tab separated format, basic text files. So you can think about, in the early days of computing, how did people store data? They stored it in the most simplistic, most intuitive way. So they made tables, lists of things, and the lists had rows and columns. So you could think of them as tabular data. So everybody knows what this stuff looks like intuitively. So I can pull up I have a little bit of data here I can show you. So for example, a patient's file in comma separated value format, it opens up in Excel because Excel is associated with that format. But you can see it has rows, it has columns, it has a header that names each type of data. Data can be dates, it can be text strings, it can be just single characters, it can be numbers like latitude and longitude. So this is Excel formatting this nicely. You can imagine a more raw experience where you open it in something like a simple text editor. It's Windows, Notepad on Windows, text edit on Mac. This is what it looks like in its simplistic rawest form. This is a row, it has columns, and there's a carriage return. So it's just a big sort of output of very raw formatted data, and each column is separated by a comma. So that is what they call the delimiter, and that's what separates one column from another, and that's how the computer can figure out that column A is the ID field, whereas column B is the birth date, column C is the death date, and so on. The only difference between a comma separated file and a tab separated file is that the delimiter character is a comma or a tab. So any character could be a delimiter, but generally columns are separated by commas or tabs. What they discovered after some time is that you would open up these files And you could see it, but it wasn't very descriptive. So they said, well, can we do a little bit more? Can we help the person understand the data? So that, and I'd probably say that the mid-1990s XML formatted data became a thing. So if you click on this link, you can see an example of that. This data is coming from HL7, which is an organization that keeps track of healthcare data. So you can see they took patient data and they broke it down and they put it between kind of these markup tags. So the name tag, Peter James, the address tag, 534 Pleasantville, et cetera, et cetera. So this is a little bit more readable because if you didn't know what column 3 was, and you could maybe infer that from the markup around it. And that's great. People use that for many years. I'd say an entire generation of software was produced based on XML formatted data. But what happens is that, otherwise small files become very large files because they have all this kind of fluff around them that adds to the cost of the file as far as storage and transmission. And so people wanted something that was similar to XML, but a little bit more efficient. The reason it was a problem is because you would have to send data back and forth, and at the time of XML's development, it was still somewhat expensive to send large files back and forth over the internet, so they wanted something a little bit more efficient. However, they wanted to preserve what's called the nestability of the data so that you could have something that wasn't just a simple table but could have sub-objects down below with more of a tree-like approach. So the emerging standard that came out probably mid to late 1990s was JSON, which was JavaScript object notation format. So the same data can be represented in JSON. So you can see here, this is the exact same person, patient type data. It's a little bit more compact. It has a key and a value just like the XML one did, but it's less space intensive. It's a little bit more cryptic looking because it has curly braces and brackets, but essentially it's the same as XML, and with the added benefit, that's a little bit more efficient. So I was just in the mechanic shop the other day getting my car serviced and saw this sign. You can have 3 things. You can have good, cheap, or fast. Only 2 of them can you have at the same time, though. So it's sort of the same thing with data. You can have something that's pretty readable, and have something that's fast for the computer to transmit or process, or you can have something that's standard. So I'm not aware of any format that has all 3 of those things. I think JSON is closest to that, and that's why it's emerged as the #1 standard. The other ones are still pretty good. You'll still run into them, but if you're thinking about the most common objects, these are the ones that you'll run into. The other thing I want to note about data formats is that you don't just standardize the format, you can also standardize the schema. So the schema is how you organize the data on if you think of it like the computer file as a blank canvas, how do you name these things? In the case of like HL7 or FHIR, they're calling this thing resource type patient. It could be something else other than resource type with a capital T. You could call, gender something else. You could have birth date with a capital B. But you need to have standardization so that standardized libraries can read this stuff in and process it without having everybody needing to reinvent the wheel. So these groups that try to establish these industry standards like HL7, they standardize not just the format, which is JSON, they standardize the schema. Now, the last point I want to make on data formatting is that there's the format and the sort of the file, and that's persisted somewhere, but it needs to be transported and consumed generally somewhere else. So that the transportation aspect has emerged over time as a technical problem. It was originally solved maybe in the 1970s where you had networks of mainframes and terminals. People typed into them. You probably remember scenes from like in John Wick or The Matrix where you have these green screen terminals. People are typing back and forth, and there's a program like IBM DB2 responding to those requests. In the 1980s and 90s, that became more of a local area network phenomenon. You had Oracle databases and Windows servers. Then the internet came out, which connected all those networks together across the world, and you had web server products come out, Microsoft SQL Server, Postgres, that type of stuff. An entire generation of internet applications was really built on those sort of PC era products. And then around 2010, we had some new innovation moving from those SQL-based products to NoSQL products like MongoDB and later things from Amazon like DynamoDB. There, the emphasis moved from having tabular data in columns with SQL statements to try to simplify that a bit and just dump everything into a common document format, largely based on JSON. So that was easier for developers. The initial products were faster and they could scale better, and that's how those big products like Facebook could scale to the level they needed to get to. And then lately, as the products have converged in functionality and cost, we've stopped caring about it so much, and now we just access data through what we call an API, which is product and vendor agnostic. So we don't care so much about the vendor, whether it's Microsoft or IBM or whether it's open source or commercial. We just want to access it using a common format, and that's generally emerged as what they call the REST or the GraphQL API approach. So we'll segue over to APIs. We can get more into this in class if you have more questions about these technical details, but we'll keep on trucking here. So the point of an API is that, without an API, you have to have access to the data, what you might call natively, which is usually difficult. You don't have a terminal to the mainframe in your house. You just don't have that stuff. You don't have it for security reasons. You don't have it because they're expensive, because they're outdated. And just like you don't have a terminal to Chase and you don't have a connection to all these data sources. But what you might have is they might say, well, I recognize that Matt really has a valid reason, so I'll expose an API to him and his company so that he can access his data for the sake of making a payment or something like that. So they do it for security reasons, they do it for control reasons, and mainly they also do it because they want to expand the ecosystem, expand the appeal of the product. So we are generally consumers in an API system. We just want the data in its purest form, and we don't care about how it's delivered. From the perspective of the provider of the API data, their job is to deliver the data in such a way that their customers can access it easily, while also taking care of security, transparency, confidentiality, making sure that they can get it fast enough. And generally that's captured in what's called a service level agreement. So for example, Amazon might guarantee that the API will be up 99.999% of the time, and you'll get a response within, let's say, 500 milliseconds. And if they don't meet that agreement, then they owe you money. So if you make a promise like that to your customer, that's called your service level agreement. And as a customer, you hold your data provider to that promise. So how do you use an API? Well, generally, you use it the same way you use a web browser, which is to have a URL. Now, sometimes the URL, the Uniform Resource Locator, is not very intuitive and can get a little messy. But the reason we use the HTTP protocol and the same web browser type technology for things like Fire is that no technology is more scalable than the HTTP protocol is. All the investment in the past 20 years has made it so that cloud providers or general service providers can access petabytes of data using a wide variety of systems, and they can deliver trillions of transactions per day, thousands or millions of transactions per second. So there's really nothing more proven, nothing more safe, and nothing less expensive than HTTP protocol. So I'm going to show you some API calls using this thing called Cynthia, which is a synthetic data provider, and they expose a FHIR standards compliant API for things like patient data. So you're probably wondering, why do I care? Well, generally it's because you're going to be working with patient level data. You're going to be doing public health problems. You may have questions about who you have in your panel, these types of questions. So I'm going to do it from the most basic level up, which is the command line, and then you'll see how that translates into something very easy and something very approachable using a tool called Postman. So here I'll pull up my command prompt in terminal, and just to kind of review, like if you go to the web browser, you type in a URL like www.google.com, and you get data back through your web browser. If you look here, you can see that there's really an HTTP in front of it. It's not showing it. There you go. It's showing the HTTP protocol, // then the host name, and then there's nothing back here because it's the top of the URL. So I can do that the hard way through terminal. I can say telnet www.google.com on port 80, which is the HTTP port, right? And it says I'm connected. And I say get, which is my verb, HTTP verb, and I say get /, which is the top level root. And what comes back is a bunch of stuff. So this is all the stuff that would otherwise power my page. So I opened what's called a socket connection. I made a request, get /, and it gave me back all this stuff, which is the HTML that makes up this page here. So you can see all the little bits of code and stuff. So it's a whole bunch of stuff, but to you when it comes up out of the screen, it's this, right? So you ask for something, you got something. Now, if we do the same thing, we can imagine that there's a better way to see that than terminal, but there's this program called Postman. So Postman does the same thing. It lets you do get, and it lets you put in your requests, and it lets you keep track of all these things together. So for example, what I'm going to do now is I'm going to start making requests to Cynthia's Fire API. So I'll just give you a little bit of background in case you want to play with this yourself. Cynthia is a product from Massachusetts. They have a synthetic data set of 1 million Massachusetts-like patients, and they expose an API to you for free, which looks like this. So there's, just like with Google, there's HTTP. This is the host name. This is the rest of the URL, version 1, Fire, and then patient. It's the patient API. In this case, it's going to give you 100 records, and it requires an API key. So they don't let anybody access their API. You have to have a key. That's what they use for security. So for example, if I'll take you here to my Postman call, so what I can do with this here is I can do the simplest thing, which is to get 100 patients. So I give them my key. I tell them I want 100 patients. I build a URL that says count equals 100, API key equals this. I do send, and then it looks like it takes a little bit of time, 4.13 seconds. And then I get back this JSON data, which we talked about before. So what's in this JSON data? All kinds of information. You can see it's not necessarily organized super obviously. It's starting with the address for whatever reason, Carver, latitude, longitude, postal code, state Massachusetts. So within each of these little curly braces, there are objects that are for, located in the patient. If I keep searching down, I can see the birth date. I can see the language the person speaks, Portuguese, whatever. Looks like the person's white, not Hispanic. All these little bits of information that would be in the person's health record. It could even have things like social security number, and you might want to think twice about how you display social security number information in a database, but it's all here, driver's license, so on and so forth. Not just for this patient, but for 100 of these patients, and that's why it's over 21,000 lines long. So with an API, what you do is you just change parameters and you get back the information you want. So for example, I can change this count parameter to 5, and I'm only going to get 5 records back. So we start thinking of these parameters, the params here in Postman, as the things that we send to the server to get what we want. So here's another one. This is a query for patients between the ages of 18 and 70. So I send in a birth date parameter, so greater than 1947, looks like less than 1999, okay, because that's probably not exactly right for 2021. It must have been written a few years ago. I still give them my count number. I still give them my API key. If I send this one, it's going to restrict the result set to those parameters, and I'll only get people within that age range. The Cynthia data set has other things that are cool too. It has, for example, this procedure code. So this would be a patient who has had procedure code, whatever this is, 112790001, which if I look back here, I think that corresponds to having an endoscopy. I submit my API key and I tell it I want three patients. And so the little hamster runs in the background and I get back my patient record for that, right? So you get the idea of how you interact with an API. This Postman is giving you a nice, pretty interface. You still need to know the documentation, though. You still need to know what's the procedure you're looking for. Now, there could be a friendly API that has, friendly procedure name, and you type in endoscopy, and it figures it out for you. But this particular one requires you to know the code. So maybe you're a physician and you want to know all the people on your in your panel or in your hospital that have had an endoscopy that are between the ages of 18 and 70. So you would stack these variables on top of each other. So you'd send the procedure variable as well as the birth date variable. And maybe there are other things too, like the zip code has to be within, 50 miles of these latitude and longitude points. And so your API interface gives you the power to get exactly the data you want. So we can't spend too much time on APIs, but the point of them is that they exist to support your needs, right? You're a physician, you have a valid need for this data. data provider is giving you the tools that you need, and if not, you need to be able to work with that person or that company to get the data that you need to solve your health problem. All right. So you can imagine that you've kind of progressed through this exercise. You've become familiar with data formats. You've become familiar with APIs, and now you get a call, and your residency director says, hey, so-and-so, I know that you're sort of up to speed on the technology stuff. We have some data analytics projects that I think you'd be a resource on. So, what is he talking about? Or what is that? What's that mean director talking about? Well, what is data analytics? So first of all, we could say, well, it's got data in it, but what other kind of data is there? So the other data that's relevant is transactional data. So think about transactional data as the raw data that the company uses for its day-to-day operations. So that could be, all the cars that are sold out of the Michigan plant, or it could be all the billing transactions to Visa and MasterCard for that day. That's the raw data. Generally, the transactional data is what you perform the analytics on. So there are people who focus on transactional data and doing that as well as possible. That's not you in this case. The other thing that data analytics isn't exactly is statistics. So statistics would be something where you focus on sampling as an understanding of a greater population. You're focusing on, testing hypotheses and inferences. Whereas I think data analytics is a little bit different here. So there are two definitions that I have for you to think about, because of course no one has the canonical definition of data analytics. It's somewhat of a new term, somewhat broad. So analytics, the process of inspecting, cleaning, transforming, and modeling available data into useful information that can be understood by non-technical people. So I underline non-technical people because generally as an analytics provider, you have a consumer in mind, an end user. Maybe it's someone in Congress. Maybe it's your manager. Maybe it's someone up the line in the business that has a question about how operations is going and what we need to do better. So there's a process there, and that's why I focused on this little quote, a process of inspecting and cleaning. So there's a question of quality. Is this the right data? Do we have accurate data? Is this data reliable, et cetera? Transforming, augmenting, that type of thing, making the data somewhat different than what it naturally comes in, transforming it to make it better, and modeling the data so that the right data is used for the right question. So that's a distinction from statistics or transactional data. There's another one that I think is fairly articulate from CIO magazine. Data analytics is a discipline. So I underline discipline there, which is focused on extracting insights from data, including the analysis, collection, organization, and storage. So the idea here is that data analytics is a bit separate from computer science or from other statistics and that type of thing. It's a discipline unto itself. It has its own tools and methodologies. And the reason that discipline exists is because we want to extract insights from data. So there's a bit of art and science there to extracting insights. It's the data don't tell you the insights. It's not self-evident. So you have to take your tools and methods, apply them to extract the insights from the raw data. And then when you do that through analysis, collection, organization, and storage, you get to the goal of data analytics. So generally, I like to think of the end product. What is the end product for data analytics? Well, generally, I think the way to think of it is you're going to deliver a narrative with one or more visualizations. Right now, visualizations, as you'll see, something like a dashboard. You'll tell a story. You'll display compelling visuals, hopefully that are data-driven, hopefully real-time, fresh data. Maybe it's charts, graphs, key performance indicators or KPIs that support your story. You're probably persuading them of something, or you're telling them something that they don't know, and you're using data to do that more efficiently. So there's a couple examples you can click on in your own time here. So here's a pediatrics dashboard that I found on the Tableau site. It's telling you all about, babies in the emergency room, where they're doing, how long patients are staying, and you're trying to put all kinds of data in one place and then let people go in and click on it and manipulate it and things like that. There's other examples in the Tableau dashboard showcase that you can click on. So as I say here, a good data analytics powered visualization, it's supposed to be pretty self-explanatory. It's supposed to close the sale by itself. So without going through the effort of data analytics, you wouldn't have that deliverable and you wouldn't have leveraged the power of your data, your raw, unprocessed, transactional data to get to where you want to be. So let's go from there. I'm sure we'll have questions and talk about that. But before I leave you on data analytics, there are some things that you should look at. These are sort of important in some sense because they're tools that are affecting not just medicine, but industries across the economy, government, every nonprofit, all sectors. So just like when word processors came out, it was a general purpose tool. It's not just for secretaries. So tools like Salesforce, Tableau, AWS QuickSight, Snowflake, Microsoft Azure Synapse, these are tools that are going to change the industry and change the economy. So to the extent this is interesting to you, you should be aware of these particular products as examples and as leaders within the industry. There's other companies as well, other little subsectors of data analytics or data management. You can dig into those as well to give you some good things to look at. So, all right. So from data engineering, we often run into a roadblock. So imagine your progression. You had some data experience with APIs. You're given a task. Your residency director says, I want you involved in this project. Great. Okay, here's some data. But there's a problem. Generally, the problem is that the data you have is in too raw of a format, and it's not what you would call fit for purpose. So fit for purpose has become sort of an industry term there that you need to have data that's fit for purpose. And so to get from your raw data to fit for purpose data, there's a bunch of steps which we might think of as the data engineering. So I'll give you an example of that here, and I'll take you through a little exercise. And I want you to take two things away from this exercise. One is that it's work. Two, that it's value-added work, and so it deserves respect. And three, it's not impossible. So you shouldn't have the view at any point in time about data analytics or data engineering that this is something that you can't do because you're not technical enough. You may not be highly motivated at any given moment of time to do this work, but it's very doable work. You know, you're physician students, you're in the top 1% of the population as far as sort of intellectual firepower, and you usually have economic resources to solve problems. So tools exist out there to solve these problems for you or to help you solve these problems. So the example that we're going to use today is sort of a setup for the work we're going to do in class. We're going to do a COVID-related exercise. So you probably have seen, dashboards out there, like the Johns Hopkins dashboard that talk about COVID rates by country and by city and that type of thing. So I have some files here. Let me find them for you. So here's an example. This was our patient's data. So here we have COVID data that comes in from this One World COVID data source. So it has data by zip code, by country code, by continent, total new cases, total deaths, all sorts of data. Here we have, I don't know how many, hundreds of thousands of rows from daily data, all sorts of statistics going out, dozens and dozens of columns. Okay, so you've gotten this data. And what we'll say the task today is to make a map, to make one of those pretty maps that we've seen so many times where you can click on the map and see the data. All right, so let me see. I even have one of those for you here. Close this one. So something like this. This is the Our World in Data map. So you click on United States. Oh, look, there's 138 cases, 138,932 cases per million. So you want to make a map something like this. And maybe you've been given a data set. But your problem is your data set doesn't have the latitude and longitude information that you need to make the map. So what do? You have to go online, you use your Google foo, right? Googling skills, and you're able to come up with a table that has all the latitude and longitude coordinates for given countries. So in this case, for example, the ISO code for Afghanistan is a country on the map, right? It has a certain point that you use for the X and Y coordinates or the latitude and longitude coordinates on the map. So how do you make it so that each row of this data gets the right coordinates so that you can then build your map? So, all right, it's a problem. You probably don't know how to do it off the top of your head, but there's tools available. So I'm going to show you this tool that I used to solve this problem, which is called Tableau Prep. So what we did here is we had the original OID COVID data. You can see it's there, right? Here's a sample of the data, right? Let me see. And then we brought in this countries code data. And as you can see here, it has the Alpha 3 code, which is like AFG for Afghanistan. And then it has the latitude and the longitude. All right. So what we want to do is we want to do a join. We want to join these two tables together into one data set. So this Salesforce Tableau Prep is a utility that's free to academics, students, and teachers. So it's not even that you have to pay for this one. So what we do here is we say, we make a join clause. We're going to join ISO code to Alpha 3 code. And we didn't even have to know any SQL. All we need to know is the columns that we want. And we can pick the column using the tool here. So you can see the tools on the left-hand side shows all the columns for the OWID COVID data. We pick ISO code. And it shows all the columns on the right for the right data set, which is the countries data set, and we pick Alpha 3 code. All right, so you can see it even shows you right here that they line up. So ABW, I have no idea what that one is. Maybe this is Angola, Albania, etc. They all line up and they're pretty much the same, so you can be sure that you're not going to run into too many cases of missed data. And then it shows you the join results. So now you have the ISO code here. Let's see, I'm going to scroll down a little bit. So Laos, right? Scroll, 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 lots of variables, lots of variables, lots of variables, poverty variables, more variables. Oh, look, and now it added on in orange. See, this is the orange data set. This is the blue data set. So it's like it just stitched on all these orange values for Laos, and it knows that the average latitude and the average longitude for Laos is 18,105. Okay? So it did that for all these tables. I mean, all these rows in the table. So just magically, Tableau Prep solved your problem and let you join two data sets together so you can build your chart. So we have the join operation, and then we have the output operation, and then what that does is it saves the combined data set to a file. And I'm going to use that file in the live real-time class exercise so we can build our map together. So I pointed out data engineering and went through this exercise with you to show you that the problem exists, it's important, but it's solvable. So hopefully that makes sense, and we'll be ready to move on to the real-world exercise in class on Tuesday. So coming to an end here, only one more slide to go before you get to go enjoy the rest of your weekend. So in class on Tuesday, we're going to use this product, AWS QuickSight. So AWS QuickSight is a part of the Amazon Web Services family of products. It's their data analytics product. It's tailored towards small to the largest companies, and it has what's called the SPICE engine. So SPICE is something short for super powerful in-memory, in-memory compute engine. And so it's kind of silly, but it actually is quite relevant because something like SPICE is necessary to do data analytics in the way that we're thinking about it. So up until very recently, maybe 5 years ago, there were data analytics products like Teradata, Oracle, IBM Cognos, but they were very expensive, complicated products. And so it's something that only the largest companies would use. So the point of this slide is to think about, what are the barriers to analytics and how has products like AWS QuickSight solved them. So I break them out into, it looks like 4 different categories. So there's the storage of the data itself, and its acquisition and manipulation. So in the case of the COVID data set we're going to use, it only has 130,000 rows. However, real world data sets would have millions or billions, possibly trillions of rows of data. So the data table or the data stream, it wouldn't just be 30 megabytes in size, which I think this one is. It could be gigabytes or terabytes in size. Okay, so you have to imagine if you want to do analysis on data, you have to be able to hold that data in memory. So traditionally, you would have memory based on sort of your non-volatile memory, the RAM in your computer, which my computer has 32 gigabytes, and that's a fair amount these days. Only recently have we had access to that kind of storage. But even that much memory, let's even say 128 gigabytes, is not that much compared to the data sets that we're talking about. So you'd have to traditionally store them on hard drives. So hard drives were the predominant method of storage until about 2010. Lately, we've had SSD drives, which are a couple orders of magnitude faster, but they're still not as fast as your memory or your RAM in your computer. So what Spice does is it processes all the data in memory. So normally you wouldn't be able to buy a computer that has 500 gigabytes of memory, so Amazon rents it to you. And it says, okay, I'll hold your data set in memory, and that'll let you process your data set basically instantaneously, or at least hundreds of times faster than what it would otherwise be, so you can do this data analytics, and you get a satisfying result. So the memory problem is the first thing. The second thing was compute. So in the old days, you'd have a server that had 2 processors on it, maybe it had 8 cores. It would still take hours or days to run through these data sets. But Amazon has solved that problem for you too with elastic computing, and it will sell you a server or a cluster of servers and rent that to you on demand. So when you click on the button for Italy and it has to run through 500 million records for Italy, it's just sharing a very powerful computer in the background with you, both its memory and its CPU, so that that question gets answered in a second rather than taking a week. So this idea of on-demand storage and on-demand computing, what that really translates to is that you don't have to wait. So analytics used to be very much a waiting game. So the results you got were not fresh. They were based on a batch that happened last night or last week. And so now the answers that you're asking are being answered in real time rather than already being out of date. The third bullet there, employee skills. You used to have to hire dedicated professionals to run your Teradata or your IBM RS6000 cluster, whatever it happened to be. So small businesses wouldn't have access to that. So even large businesses like, let's say, Presbyterian St. Luke's, they may have general purpose servers, but they wouldn't have the $10 million Teradata server at their offices here in Denver. But now they can sign up for Amazon QuickSight, and they can have access to that, and no one has to manage that. So we have the direct product costs, things like servers and licensing fees, kind of touched on that. Amazon's model is $8 per user per month. So you turn on a user, you pay $8. Next month you don't need them, you turn them off, and you don't pay anymore. So this compares to either the millions of dollars that you would have to pay for traditional hardware-based solutions, or even relatively recent cloud-based solutions like SaaS. There's a SaaS product called SaaS VIA or SaaS Visual Analytics. They charge $5,000 to $10,000 per year for an individual user. So what that means is that the SaaS product is limited to power users, maybe 1 or 2 users within a company or in a department, whereas something like QuickSight is much more democratic in nature. And now almost everybody in the organization can use and leverage data, can create these types of dashboards, and can be a participant in the data ecosystem. So that now the data ecosystem is a much more densely connected mesh versus just a kind of a sieve that a lot of ideas and concepts fall right to the bottom on. Lastly, there's training costs. Everybody knows how to use a web browser. They can kind of power through a product like AWS QuickSight, and as you'll see in class, it only takes maybe 15 minutes to half an hour to do basic things. So otherwise, you have to spend thousands of dollars for training, certification, all that type of stuff. So as I hope to demonstrate next week, when we do all these exercises together, there's sort of a sea change in cloud analytics that's made possible by these changes. It's going to let you do amazing things that could never be done in the past. You'll be able to solve all sorts of problems from data engineering because you have the fundamentals. And hopefully you'll be able to be like Jon Snow and use your data analytics background and your critical thinking to solve important problems. So that's it for right now. I'm going to stop here and we'll pick up on Tuesday. Thanks, guys.